Welcome to the next session of subject Engineering Maths. We were discussing chapter 3, that is we start in this session integral calculus of the calculus concept, definite integrals, followed by some classroom workbook questions based on definite integrals. Okay. So in the calculus we were discussing subtopic, that is integral calculus. This is actually second part of calculus. Differential calculus is finished. Now this is integral calculus. We start with the definite integrals. Suppose we have a function f of x. Assume that this is continuous in closed interval a comma b. Since a function f of x is continuous in closed interval a comma b, the graph of f of x is continuous in closed interval a comma b. So when you draw the graph between the boundaries x equal to a and x equal to b, the graph will have no breaks at all. Now let us see the structure of continuous function f of x in closed interval a comma b. Suppose the graphical representation is like this. This is a two-dimensional coordinate system, x-axis and y-axis. Suppose the graph is like this. Now this is A and this is B. This is A and this is B. Now this curve is nothing but y equal to f of x. Now draw one line. This is actually x equal to A. Draw a line parallel to y-axis. This is the line x equal to B. And this shaded region is a finite value, that is it gives a finite area, and this finite area we denote it as symbolically integral a to b f of x dx. This is the geometrical representation of a definite integral. I have a function f of x which is continuous in closed interval a comma b. So in that case integral a to b f of x dx is nothing but area bounded by the curve f of x between the lines x equal to a and x equal to b. So what it represents geometrically, it gives a finite value. That value is nothing but area bounded by f of x between the lines x equal to a and x equal to b. Therefore this integral a to b f of x dx is nothing but area bounded by f of x between the lines x equal to a and x equal to b. Let us take one sample example. Suppose we have integral 1 to 2 x square dx. Now integral x square is x cube by 3. Limits are from 1 to 2. Now apply the upper limit 2 cube 8 by 3 minus replace x by lower limit 1 by 3. So this is 7 by 3. So basically this 7 by 3 is nothing but area bounded by x square between the lines x equal to 1 and x equal to 2. So let us draw the graph of this two-dimensional coordinate system. The graph of x square is a parabolic shape. Now this is the line x equal to 1, and for example this is the line x equal to 2. This graph is nothing but y equal to x square, and this shaded region, this is nothing but 7 by 3 square units. Okay, so note this point. Let y equal to f of x be a function. Let y equal to f of x be a function which is continuous in closed interval a comma b. Let y equal to f of x be a function which is continuous in closed interval a comma b. Then integral a to b f of x dx. Then integral a to b f of x dx is nothing but area bounded by f of x between the lines x equal to a and x equal to b. Is nothing but area bounded by f of x between the lines x equal to a and x equal to b. So draw this graph and illustrate this by taking an example. followed by this graphical representation. Now, as we discussed, it gives area bounded by f of x between the lines x equal to a and x equal to b. Now, practically, it may not be simple to evaluate this directly by drawing the graph. So, therefore, in order to evaluate these different integrals, we have some properties. And before discussing properties, let us discuss few definitions to get these definite integrals. So, we discuss definition of even function. Suppose we have a function f of x whose domain is capital D. That means for all values of D, f of x gives some finite value. So when f of x is defined in domain D, we say that this is an even function if f of minus x equal to f of x for all x belong to D. So whenever this happens, f of minus x equal to plus f of x, then we say that f of x is even. Of course, it must be true for all x belong to D. So replace x by minus x. It must be same as original function f of x, and this must be true for all x belong to D. So whenever this happens, we say that f of x is an even function. Let's take an example. Suppose f of x equal to x square. Now here the domain of this function is R. For all real numbers, x square is a finite value. Now when you replace x by minus x, this becomes minus x whole square. Minus x whole square is x square. So here this is f of x. So f of minus x is f of x for all x belong to R. Therefore, this is an even function. Because of this even power, x square is an even number. When you take f of x equal to cos x, here the domain of cos x is again real numbers. Now replace x by minus x. This is cos of minus x. This is again cos x. Because when you go to series expansion of cos x, it contains only even powers of x. See, the series expansion of cos x is this. 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus and so on. So therefore, the series expansion of cos x contains only even powers of x. So even when you replace x by minus x, you get back the original quantity. Therefore, in this case, when you replace x by minus x, again you will get cos x. So therefore, this is f of x for all x belong to R. Therefore, this is an example of even function and this is an example of even function. Okay, write the definition. Even function. Let f of x be a function defined over a domain D. Let f of x be a function defined over a domain D. Let f of x be a function defined over a domain capital D. We say that f of x is even. We say that f of x is even if f of minus x equal to f of x for all x belong to D. If f of minus x equal to f of x for all x belong to D. Work out example 1 followed by example 2. Next we move to odd function. It is similar to even function. We have some small changes. We have a function f of x defined over domain D. We say that this is odd function if my f of minus x is minus f of x for all x belong to D. Replace x by minus x, you must get minus f of x for all x belong to D. So in that case, f of x is said to be an odd function. So examples, instead of taking even powers, let us take odd powers. For example, 3. Then f of minus x is minus x whole cube. Minus 1 whole cube is minus, this 2 becomes 3. So therefore, this is minus f of x. So here when you take odd powers of x, they will be odd functions. F of minus x is minus f of x for all x belong to R. When you go for trigonometry functions, instead of sin cos, let us take sine function. Sine. Now when you replace x by minus x, this becomes sine of minus x. Here this is a minus sine x. So this is a minus f of x for all x belong to R. Why it is happening? Why sine of minus x is minus sine x is the series expansion of sine x is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus and so on. It contains only odd powers of x. Since it contains only odd powers of x, when you replace x by minus x, minus comes before that x. Therefore, sine of minus x is minus sine x. So, f of minus x is minus f of x for all x belong to R. Therefore, this is a trigonometric odd function and this is a polynomial expression x cube. This is again an odd function. Okay. So, write these points. Definition: odd function. Let f of x be a function defined over a domain D. Let f of x be a function defined over a domain capital D. We say that f of x is odd. We say that f of x is odd if f of minus x equal to minus f of x for all x belong to D. If f of minus x equal to minus f of x for all x belong to D. Now note down example 1 and example 2. Now we discuss some results based on even functions and odd functions. Suppose I have two even functions. One is, for example, f of x and another is g of x. F of x is even, g of x is even. Add these two, you will get a new function. That is f of x plus g of x. Will it be even? So what my statement is sum of two functions even or not? If so, we need a proof. Right? Is sum of two even functions even or not? Suppose when you apply this result for even numbers, suppose x is an even number, y is an even number, then x plus y is an even number. Yes or no? So in the same way, sum of two even functions will be again an even function. Let us discuss with a sample proof. Suppose we have a function f of x, which is an even function, and g of x is another function. Even this is also an even function. So take h of x equal to f of x plus g of x. So that means sum of these two functions is h of x. Now let us prove that h of x is also an even function. So replace x by minus x. This becomes f of minus x plus g of minus x. Here f is an even function. Therefore f of minus x becomes f of x. G is an even function. So g of minus x is g of x. So therefore h of minus x is h of x. So we got the result as h of minus x equal to h of x. Therefore since it is even, there is sum also an even function. Therefore sum of two even functions is again an even function. This is the proof. Note. Sum of two even functions is again an even function. Sum of two even functions is again an even function. Now let us discuss the same result for odd functions. Suppose when you take f of x odd and g of x odd, will its sum be again odd function? Certainly, the result may not be true in case of numbers. Suppose I have an odd number, x value is 3. This is odd number. Y is an odd number, this is 5. This is also odd number. But when you take x plus y, you will get 8. This is an even number. So therefore, sum of two odd numbers is even number in case of numbers. But is this valid even in case of functions? Let us see. Suppose f of x is odd function. G of x is odd function. Now add these two, call the resultant function as h of x. Let us see whether h of x is odd or not. So replace x by minus x. H of minus x is f of minus x plus g of minus x. Since f is an odd function, f of minus x becomes minus f of x plus, since g is odd, g of minus x becomes minus g of x plus into minus minus. So this is minus f of x minus g of x. Now take minus common. This is minus of f of x plus g of x. Therefore, this is nothing but minus h of x. Therefore, the result we got is h of minus x is minus h of x. That means h is again an odd function. So the result is sum of two odd functions is again odd function. Note, sum of two odd functions is again an odd function. Sum of two odd functions is again an odd function. This proof is not required. Now let us combine one even function with one odd function. One even with odd function. When you take numbers, suppose x is even number 2, y is odd number 3. Add 2 and 3, you will get odd number. So in case of numbers, sum of even and odd numbers is odd. But let us see in case of functions. So suppose f of x is an even function. G of x is an odd function. Add these two, call the resultant function as h of x. So h of x is f of x plus g of x. So let us know about h of x. So replace x by minus x. H of minus x is f of minus x plus g of minus x. Here f is an even function, so f of minus x is f of x. G is odd function, so g of minus x is minus g of x. So when you replace x by minus x, we were getting f of x minus g of x. Here this is not equal to h of x, because h of x is this. In case of h of x, we have plus between f and g, but this is a minus in between f and g, so this is not equal to h of x. Even the same expression is not equal to minus of f of x plus g of x. So therefore, whenever this result h of minus x is h of x, we call it as even function. If it is a minus of h of x, we call it as odd function. But unfortunately, in this case, it is behaving very differently. H of minus x is not equal to h of x, and h of minus x is not equal to minus of h of x. Therefore, when you add even function with odd function, the result is neither even nor odd. Let us take one example. Suppose f of x equal to x square. So this is an even function. G of x equal to sin x. This is an odd function. So take h of x equal to f of x plus g of x. Therefore, this is x square plus sin x. Now take h of minus x. This is x square minus sin x. Now what I want to say is, here h of minus x is not equal to h of x for at least 1x. for at least 1x. This is point number 1. H of minus x is not equal to h of x for at least 1x. Even I can tell you x value. The value of x is, for example, you can take x value as, for example, pi by 2. H of minus x is not equal to h of x for at least one value of x. Even I can tell you x value is pi by 2. And even the second point is h of minus x is not equal to minus h of x for at least 1x. For at least 1x. Even you can take, for example, x value, for example, 1. You can easily verify. So therefore h of minus x is not equal to h of x for at least 1x, and h of minus x is not equal to minus h of x. You can cross verify these values. Therefore sum of even and odd functions is neither even nor odd. Neither even nor odd. Note this point, very important. Sum of even and odd functions, sum of even and odd functions is neither even nor odd. Sum of even and odd functions is neither even nor odd. Example, you can take this. You work out this up to the last point. Now we discuss properties of definite integrals to get definite integrals very easily. So the next concept, properties of definite integrals. We have 4 properties. Let me write out one by one. Suppose we have integral a to b k1 into f of x k1 dot integral a to b k1 dot f of x plus or minus k2 into g of x dx. Here k1 is some constant. It is multiplied with function of x. k2 is a constant multiplied with function of x. In between these two, we have either plus or minus. Generally, when functions are multiplied with constants during integration, they can be taken before integrals. They do not affect integral values. So this is k1 times integral a to b f of x dx. If it is plus, write plus. If it is minus, write minus. Plus or minus k2 into integral a to b g of x dx. For all constants k1 comma k2. For all constants k1 comma k2. And this property is called linear property for definite integrals. This is called linear property. And second result is integral a to b f of x dx is same as minus integral b to a f of x dx. What we have done is, here lower limit is a. So now it becomes upper limit. Earlier b is upper limit, now it becomes lower limit. So when you interchange the limits, minus symbol will come. When you interchange the lower and upper limits, minus will come extra. Now property number 3. Integral 0 to a f of x dx. We are integrating this function from 0 to a. This will be equivalent to integral 0 to a f of a minus x dx. Integral 0 to a. Same limits are working, integral 0 to a, but x is replaced by a minus x. Generally, people think that this is complicated when compared to this, because unnecessarily we are replacing x by a minus x. That means unnecessarily we are making a function so complicated. But there are some advantages by replacing x with a minus x. Okay, so you can understand very easily during classroom workbook questions. But when you replace x by a minus x without changing limits 0 to a, this integral and this integral will give same value. Now let us go for property number 4. This is also very important. Integrate the function from minus a to plus a. Integral minus a to plus a f of x dx. So when you are integrating a function in the closed interval minus a comma plus a, minus a to plus a, then check whether it is even or odd function. If it is odd function, then its value is 0. So this integral is 0 if f of x is odd. If f of x is odd. Suppose if it is even, then this becomes 2 times integral 0 to a f of x dx. So this integral becomes 2 times integral 0 to a f of x dx if f of x is even. If f of x is even. Suppose if f of x is neither even nor odd, then split the integral by using linear property and apply integral separately for even function and apply integral separately for odd function. But if it is luckily either even or odd function, you can apply either this or this. If it is odd, value is 0. If it is even, integral becomes 2 times integral 0 to a f of x dx. Okay, so all these properties are very useful. Mostly we use properties 3 and 4 very commonly to solve many questions. Note down all these points.